Hi, my name is Bin. Today I will present RadarNet, a new approach that exploits radar for robust perception of dynamic objects. Different sensors are used for self-driving. Cameras are cheap and provide rich semantic information about objects in high resolution. However, they do not provide direct depth information, making 3D perception difficult. Furthermore, image quality is sensitive to lighting conditions. LiDAR, on the contrary, provides accurate geometric information and is invariant to the ambient light. However, the LiDAR has limited resolution and it is sensitive to weather conditions such as rain, snow, and fog. While cameras and LiDAR capture the static information of the environment, radar provides additional velocity information. Compared with LiDAR, it also operates at a longer range and is more robust to weather. However, radar data is more sparse and noisier than LiDAR. Previous works exploit radar to a limited extent. Some treat radar as point clouds and propose different fusion mechanisms. In these methods, radar provides depth for image-based perception, which serves as a cheaper alternative to the more expensive LiDAR sensor, mostly in the context of ADAS. However, these systems cannot match the performance of LiDAR-based ones. Alternative approaches take radar as object detections and perform sensor fusion at the track level by performing simple object association. These approaches typically provide higher object recall by combining results from different sensors. However, the complementary information between sensors is not fully exploited, and therefore the state estimation is not accurate enough. In this paper, we focus on the setting of fusing LiDAR with radar, aiming to build a perception system that achieves state-of-the-art results. Before we go into the model details, let's first take a look at what the sensor data looks like. We first compare the sensor specifications between a Velodyne 32-beam LiDAR and a Continental radar. While radar has over 2 times detection range and additional velocity measurements, the geometric accuracy and resolution are not as good as LiDAR. We can see in the visualizations that radar data is more sparse, contains false detections caused by multipass reflections, and its position measurements are also less accurate. Based on the previous observations, we propose a multi-level radar fusion that fully exploits the geometric and dynamic information of radar data. Our model consists of 3 parts: a voxel-based early fusion module that produces multi-sensor representations, a bird's-eye view detection network that predicts object detections and their velocities, and an attention-based late fusion module that refines object velocity with radar evidence. We perform early fusion by voxelizing LiDAR and the radar point clouds separately, and then combine them in the same bird's-eye view space. In particular, we take multi-sweep LiDAR point clouds from the past 0.5 seconds as input so that the detector is able to infer object motion. We generate a BEV voxel representation where the height dimension and consecutive sweeps are both concatenated in the channel dimension. The voxel feature is the distance-weighted density, where the contribution of each point to the voxel is weighted by its relative distance to the voxel center. For radar, we take multi-cycle point clouds in the past 0.5 seconds as well, and generate a similar BEV voxel representation. The difference is that we ignore the height of the radar points, as they are usually inaccurate if they ever exist. We use the MotionAware Occupancy as a voxel feature, which is 0 if there is no radar points, 1 if there is dynamic radar points, and -1 if there is static radar points. We feed the multi-sensor voxel representation to a BEV detection network whose architecture follows PNP-net, thus extracting multi-scale BEV feature maps. The header outputs both object detections as well as their velocities. Object detection is parameterized as an oriented box in BEV space, while the velocity is parameterized by the probability of moving and the 2D velocity. During inference, if the moving probability is smaller than 50%, we set its velocity to 0. Given initial object detections, the task of late fusion is to fuse the dynamic information of surrounding radar points to the detection in order to refine their velocity estimates. Given the radial velocity provided by radar, it is ambiguous what the actual object velocity is without having tangential information. To overcome this ambiguity, we align radar velocities to object detection, where we back project the radar's radial velocity to the predicted velocity direction of the object. After velocity alignment, we compute the pairwise radar object features, which have two components. The first component contains information of the object detection, including its size, velocity, and orientation. The second component contains information of the radar target with regard to the object detection, including the position and the time offset between the radar point and the object detection, as well as the aligned radar velocity. Given the pairwise features between one detection and all radar targets, we use the learnable MLP to predict their association scores. We then normalize the scores to sum to 1. Note that we append 1 before normalization to handle cases with no association. Given normalized association scores, we then get the refined velocity by computing the sum of all radar velocities and the initial detection velocity, weighted by the scores. We train our model with a multitask loss. We apply detection and velocity loss on the outputs of the detection network and another velocity loss on the output of the late fusion. We validate our approach on the new scenes dataset, where we focus on cars and motorcycles as they have large velocity variance, while our LiDAR-only model already achieved state-of-the-art results in comparison with previous methods. Adding radar further improves the performance, especially in velocity estimation. We now show ablation studies on different fusion mechanisms. Early fusion exploits the geometric evidence from radar, especially on the smaller motorcycles, which have limited LiDAR observations. Attention-based late fusion exploits the dynamic clues of radar data, bringing around 15% reduction in velocity error in both classes, while a rule-based association method can only get less than 10% improvement. On our internal dataset, dense radar, where we evaluate at longer range, we show that the detection gain increases as a function of the object range. In terms of velocity error, we are able to achieve 19% improvement. We also evaluate our heuristic baseline for late fusion, where we design a set of rules for object radar association. We conduct fine-grained evaluation as a function of object range, number of LiDAR points, deviation angles between velocity direction and the radial direction, and object velocities. The heuristic baseline performs well in general, but fails to bring improvements in certain cases. First case is when we already have abundant LiDAR observations in the near range. Therefore, the velocity estimation from the detection network is already very accurate. Second case is when the velocity deviates a lot from the radial direction, and therefore the ambiguity caused by lack of tangential information is larger. Third case is when the velocity is small, thus further improvements require the radar evidence to have high precision. In contrast, in all these cases where the radar uncertainty is large, we see that our proposed attention-based late fusion is able to achieve significantly smaller velocity error. This shows that our approach is able to capture the uncertainty and complex dependencies between the object and the radar measurements. Here we show some examples of the learned object radar association, where we highlight the associated radar target in yellow if it has a normalized association score greater than 0.1. Note that our method selectively chooses most relevant radar points and is able to handle large noise in radar positions. To summarize, in this paper, we propose the multi-level fusion mechanism to exploit both geometric and dynamic information provided by radar sensors. We achieved state-of-the-art results in terms of object detection and velocity estimation for dynamic objects. Thank you.